This video lecture is meant to be a continuation of the video lecture that was discussing enthalpy changes of a reaction. We had already talked about how you can look up enthalpy changes on either of two reference tables or by combining heats of formation of the compounds in a reaction by using the equation the delta H is equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. And the third way is by combining equations using Hess's law. That's where we're at right now. Hess's law states that the enthalpy of a given chemical reaction is constant regardless of the reaction happening in one step or in many steps. Basically, a chemical equation can be written as the sum of several other chemical equations. And when you do that, the enthalpy change of the first chemical equation equals the sum of the enthalpy changes of the other chemical equations. It sounds complicated, but really it's like a puzzle. You're going to be given a reaction for which you have to find the enthalpy for that reaction. Okay, so the reaction you're given is sort of like, you think of it like a target equation. That's the goal, that's what you're trying to have in the end. To get that target equation, you're going to be given at least two other equations that you're going to have to manipulate and add together in such a way that it matches the target original equation. It's a puzzle that you can solve, but you have to follow these rules. You can flip the equations that you're given to work with if necessary. Of course, if you flip them, you'll need to change the sign of the delta H. Ultimately, you have to have the correct products on the right side of the arrow and the correct reactants on the left side of the arrow. You must be sure that the compounds cancel out on both sides if those compounds are not in the target equation. And you need to be sure that the coefficients match the target equation. Once you have all those items met, you have to add up the enthalpies, and that will be the delta H of the reaction. Okay, so the first reaction that we're going to take a look at is we're going to calculate the delta H, the heat of the reaction, for this equation. 2 C's, 2 carbons, plus oxygen turning into 2 carbon monoxides. So that right there is your target equation. That's our target. We're given 2 equations that we can manipulate right here, and their associated enthalpies. All right, so since we're given 2 equations to work with, here's how I'm going to suggest you proceed. Start by writing 2 arrows. These 2 arrows will represent the 2 equations that you're given to manipulate, because we may be writing them the way they're written, or we may have to flip them. So what we want to do is compare our given equations to our target equation. The target equation has carbon monoxide as a product. So let's look at our given equations. The second equation has carbon monoxide as a reactant. The first equation doesn't have carbon monoxide at all, so we're going to have to take this second given equation and flip it so that we have 2 carbon monoxides on the product side. Oxygen has to stay with it on the same side of the arrow. And then flipping the equation, we have 2 carbon dioxides on the left side of the arrow. Okay, by flipping that equation, the enthalpy sign changes from a negative 283 to a positive 283 kilojoules. Okay, so now this gives us the carbon monoxide that we need on the product side of the equation. What we need on the reactant side of the target equation is 2 carbons and a single oxygen. And if we take a look at our first given equation, carbon and oxygen are already on the left side of the equation, so we're going to rewrite that equation as it is. That has an enthalpy of negative 394 kilojoules. But if you notice, we now need to consider coefficients. Right? We notice that we want, and I'm going to erase this so we can see this more clearly, on our target equation we want 2 carbon monoxides. Well, we have that right here, 2 carbon monoxides, so that second given equation is pretty good. If we look at our reactant side, we need 2 carbons and a single oxygen, but over here we have only a single carbon. So what we're going to need to do is multiply all the coefficients of this first reaction by 2. So the implied 1 is now a 2. The implied 1 in front of the oxygen is now a 2, and the implied 1 in front of the carbon dioxide is now a 2. Okay, by doing that, we now get our 2 carbons on the left side of these equations. But when we double that equation, we will also need to double the enthalpy right here. So we're going to multiply that negative 394 by 2. Now let's take a look and see if everything else sort of works out. What we're looking for, we want to keep that, the 2 carbon monoxides on the product side. We want to keep the 2 carbons on the left side. But now, oxygen, what's going on with the oxygens? What's going on with the carbon dioxides? Well, if you notice, the 2 carbon dioxides on the right and the 2 carbon dioxides on the left will end up canceling out. And if you take notice here, we have 2 oxygens here on the left, a single oxygen on the left, on the right. So that oxygen will cancel out with one of those oxygens on the left. And now you have everything that you wanted in your target equation. So we're going to rewrite this so it's a little bit neater and clearer. We have 2 carbons plus a single oxygen turning into 2 carbon monoxides. So when you get the 2 equations to add up and cancel out so that you have the target equation, then you know it's okay to go ahead and add up your enthalpies. All right, so 2 times negative 394 gives you, this works out to negative 788 kilojoules. So then if we add those 2 numbers up, negative 788 plus a 283, we have the heat of the reaction being negative 505 kilojoules. Okay, let's take a look at a second example. Calculate the enthalpy for this following reaction. We have nitrogen reacting with 2 oxygens to form 2 NO2s. We're going to use the following 2 equations. Again, 2 equations to manipulate. Start by drawing your 2 arrows representing the 2 equations that will be manipulated. And we have to try to see what are we looking for in our target equation. We're looking for 2 NO2s on our product side. So if we look at our 2 given equations, the only equation that has NO2 at all is this first equation. But the NO2s are on the wrong side. They're on the left side. So we're going to take this first equation and we're going to flip it. And we're going to put the 2 NO2s on the right side of the arrow. And we're going to put the 2 NOs and the oxygen on the left side of the arrow. Okay? But by doing that, the heat of the reaction goes from a positive 112 to a negative 112 kilojoules. All right, let's take a look. What else do we need in our target equation? We have N2 and 2 O2s. So let's take a look and see. We have N2 and O2 on the left side of the second equation. So we're going to keep this equation the same. N2 plus O2 turning into 2 NOs. Right, so we're going to keep that enthalpy at a positive 180 kilojoules. There should be a decimal there. That's a typo. Okay. All right, well, let's take a look and see if our coefficients match. What are we looking for? We're looking for 2 NO2s on the right side. That's right there. So that we want to keep. That we do not want it to cancel out. Okay. If we see here that there are, we want an N2 on the left, we want to keep that. We have 2 oxygens on the left. Well, we want to keep those. They come from 2 different equations, but that's okay. Hopefully everything else should cancel out, which it does. The 2 NOs on the left and the right will cancel out. So when we rewrite this equation, all right, all we will need to do here is to rewrite it to clean it up. N2 plus 2 O2s turns into 2 NO2s. Okay, so we're validating that we actually got to the target equation. We didn't have any multiplying to do, so it's just a straight adding up of these 2 numbers. Negative 112 plus 180 kilojoules adds up to a positive 68 kilojoules, and that is what is equal to our heat of our reaction. Okay, let's take a look at problem number 3. I'm going to let you try this one on your own. If you want to pause the video or try it at the end of the video, that's fine. I will tell you that you can do an answer check. Hopefully you come up with the same heat of the reaction that I do here. It should work out to a positive 77.2 kilojoules. So see if you can do that one. We're going to move ahead to a slightly harder problem because now we're going to take a look at 3 given equations instead of 2. We're trying to find the heat of the reaction for CH4 plus NH3 turning into HCN and 3 H2s. Okay, we're given 3 equations. So again, what we're going to do, 3 equations to manipulate. You would start with writing 3 arrows, and we will then take a look at what we need to do with each one of these equations to get our target equation. Well, let's see. I see that one of the first target products is HCN. So go and look at your 3 given equations, and I see that in the third equation we have is the only one where there's HCN at all. So if we don't have to flip that equation because it's already on the correct side. So 2 HCNs on the right, and we are given H2 plus 2 C's plus N2s. Okay, so that equation at the moment remains the same. It has a positive 270.3 kilojoules. Okay, what we do see, however, is that the coefficient doesn't match. There's 2 HCNs here, but there's only 1 HCN up here. So we can go ahead and manipulate this equation to reflect that. To make 1 HCN, we would divide all of the coefficients by 2. So the 1 that's in front of the N2 here has to become a 0.5. The 2 in front of the carbon becomes a 1, and the 1 in front of the hydrogen becomes a 0.5. I know these are not whole numbers, but it's okay to manipulate them for this purpose. Okay, now what we want to do here, this 270.3 needs to also be divided by 2. When you do that, you're going to get a positive 135.15, and I'm not going to worry about significant figures at the moment. Let's just leave that alone for now and focus on the task at hand. All right, so right now we have HCN as a target product looking pretty good. Let's see, what else do we need to take a look at? Let's take a look at methane, CH4. CH4 in our target reaction is a reactant. Okay, the only place I see methane in our given reactions is right here, but it's on the product side. So we're going to need to flip this equation to reflect that. So we're going to put CH4 on the reactant side and carbon plus 2 H2s on the product side. So by flipping that, the negative 74.9 will become a positive 74.9 kilojoules. Now we're not going to have to do anything with coefficients because the coefficients are already good. 1 methane in the given equation, 1 methane in the target equation. So we're not going to have to multiply or divide 74.9 by anything. All right, the other substance that we could probably take a look at is this NH3. NH3 in the target equation is on the reactant side, but in our given equations NH3 only shows up once, and it is on the product side of the first equation. So we'll need to flip that equation to reflect its proper placement. So 2 NH3s on the left side, N2 plus 3H2 on the product side. Because we flipped the equation, the delta H is going to have to change to a positive 91.8 kilojoules. Okay, so let's take a look and see if we have everything nailed into place. I see that we don't with the ammonia. Our given reaction had 2 moles. Our target equation has only 1 mole of ammonia, so we're going to need to change that. So if we divide this first equation by 2, to get 1 ammonia, half of a nitrogen, and 1.5 hydrogens, then we need to also divide the enthalpy by 2. 91.8 divided by 2 gives us a positive 45.9. Okay, let's take a look at our overall equation to make sure, oops, that everything sort of cancels out. I don't know why my black pen's not working. No black pen. Okay, black's not working. All right, let's see. Our target equation. We have our 1HCN. That's good. We want to keep that. We'll come back to the hydrogens because they're kind of all over the place. On the reactant side, I've got my 1-methane. I want to keep that one. I've got my 1-ammonia. I want to keep that one. So now we have to kind of figure out what's going on with the hydrogens. We want a total of 3 hydrogens on the right-hand side. Okay, so let's take a look at that. If we see with the hydrogens, we've got half of a hydrogen here. That'll cancel with the half of the hydrogen right here. Okay, so that cancels. But then that leaves us with this 1 hydrogen plus these 2 hydrogens. So there's our 3 hydrogens. Okay, now what else is canceling? We have this 1 carbon canceling with this 1 carbon. We have this half of a nitrogen canceling with this half of a nitrogen. So it works out. NH3 is left over with the CH4. On the product side, we have HCN plus the 3 hydrogens. And we've already manipulated all the enthalpies, so the 3 numbers we're adding up are these 3. And when you add those up properly, you get the delta H of the reaction to be a positive 256.0 kilojoules. All right, so that one got a little more complicated just by the nature of the fact that we had some multiplying and dividing, and we had 3 equations to manipulate. Okay, I'm going to take you